don't like open welds. So, yeah, to introduce myself, so I currently work really far from here. It's probably at least 300 or 400 steps to get to Blue Ridge Community College. All right. So my official title is a welding faculty coordinator, so I just run the welding department. I teach a few classes, but I'm also just the welding department secretary is the way I like to put it. So I do a lot of the paperwork, and I've got a really, really solid team there, so I just have to keep them happy and make sure the department and all of our students have what they need. So previously, before this, I worked for an inspection firm. I say primarily in the Raleigh area, because I grew up here over in Saluda. And then my wife and I, at the same time we got married, we moved out there for about 3 years. I took that job, and then we came back and gone a few other places since then. But probably my main, I guess, most relevant credential is a American Welding Society Certified Welding Inspector. So I've had that since 2017. If you aren't familiar, the American Welding Society is they're toe-to-toe with ASME, right, as far as welding specifications. So the way I like to say it is AWS covers stuff that doesn't move, like buildings, bridges, not supposed to move. And then ASME covers a lot of everything else, like piping systems and things like that, like inside the building, but AWS creates the building. That's the way I like to put it. And what that credential means is that it essentially means I'm qualified to interpret any welding code, but also more importantly, qualify welders as well. All right, so if you ever heard the terminology like a certified welder, they have to go take a test. They got to find somebody like me. I administer the test, write the paperwork, and put my fancy right stamp on it. Okay, so that's my main credential. Other than that, I've been in the welding industry, basically since high school, so 2012. I've welded probably just about everything. Yeah, I'm just trying to think. Probably just a little bit of everything as far as definitely material-wise. So steel, aluminum, titanium, stainless steels, and all the other extra special stainless steels like Inconel. Some of y'all probably heard those words before. I just call it extra expensive stainless. Okay.
Nickel, chromium, iron.
All right. So, yeah, and I've been teaching off and on since roughly 2016 or 2017. And one of my favorite things about just welding in general, or y'all probably say similar things about aviation and everything, is one of my favorite things is there's always more to learn, right? It's one of the things I try to tell, because I have a lot of students that are still in high school, anywhere from 16 to 18 years old. And I try to teach them how to weld, but also just how to be a professional, right? Or just how to work or how to learn. So one of my favorite sayings is, the day that you stop learning is the day that you start declining, right? You can't truly stay stagnant. That may or may not be true, but it sounds good. Okay. But I will also admit, I'm coming here from a place of humility, because I don't have any sort of, real aviation experience. Okay. I've flown in a few planes. I've advised a few people on welding and things like that. But yeah, I did find an interesting thing. I was trying to find a good picture of it, but I was chatting with Bill over there. It was probably 20 years ago. I was involved with the EAA, the Young Eagles. Mom signed me up for it, and it was out of the Asheville airport, and I got to fly in a Long Easy, which we figured out may or may not have been Sid. It actually flew me. So I was trying to see if she had a good picture somewhere to dig up out of a shoebox, but we couldn't find one. So the question, why am I here? Well, the funny answer is Nancy and Tim invited me. So some personal connections and stuff, but long story short, I wrote a book a few years ago specifically for 4130 tubing. You can tell I did not hire a marketing expert, because I chose the smallest niche possible. Not only did I say, I'm not going to teach you how to weld, I'm going to teach you what you need to know to transition into it. It's also a very specific part of welding. But it was, I guess you could say, more like a passion project, because I got involved with bicycle frame building. That was my COVID project. What else do you do when you know how to weld and you also love mountain bikes? So I ended up building a few of my own bicycle frames, and I got involved with that community. And there's a lot of really bad information about welding online. Some of it's misinformation, some of it's the way they're taught, or just lack of understanding, right? It's kind of like another one of my favorite sayings is, you never truly understand a subject until you can teach it to anyone. And that's, again, part of what I was talking about, just continuous learning, right? When I first started, teaching at, Blue Ridge, I was, gosh, how old would I have been? Probably 24, 25, somewhere in that range. And half of my students are double my age. It was a very humbling experience. but at any rate, here's some pretty pictures here. So down on let's start at the bottom left. That's just a pretty bike picture that people like. So that's one of the latest mountain bikes I built. Top left is a chainstay yoke that I designed. This is way off subject, but with a modern mountain bike, you have a really difficult problem of rear wheel, short chainstay length, and the cranks. They all have to occupy the same place at the same time. So there's not a whole lot of good ways to solve that problem. And up there on top left is, we call it a yoke or a chainstay yoke. It's something that I designed, and again, my marketing director that's non-existent would hate me because I just published it to the community with some specifications. I was like, y'all use this. And I've seen it, people still tag me on some of the forums and stuff whenever they use it, which is a really cool experience, but it's not helping my bank account though. But it's very gratifying. Bottom right is kind of, again, like, I already forgot the gentleman's name that presented or introduced me here.
George.
Yeah, George, but as he mentioned, right, so 4130 tubing, or just chromoly, there's a lot of similarities. So as I was writing that book, it was going to be just for bicycle frame building. But then a good friend of mine, a structural engineer down in Greenville that was helping me write the book, getting me started, he said, well, why don't you see if there's any other fields? And sure enough, motorsports and a lot of aircraft building, it shares the exact same techniques. You have two round pieces, up there on the top right, you take a big bite out of them and stick them together and weld them. So you can very efficiently and quickly build a structure, that can perform just about do anything you want. Okay, so it's kind of there's a saying, you may have heard this before, I don't know if it transfers over in aviation, but in the bicycle world, steel is obsolete, okay? But there's a saying that people say, they say steel is real, okay? It's kind of mystical. They talk about the ride quality and things like that, but it's only half of the saying. The actual saying is steel is real easy, okay? You can buy steel for relatively cheap because it's almost ubiquitous now. And even a bicycle frame like that on the bottom right, you could make with a file and something to weld it together if you're really motivated. Right? I mean, obviously, we have other tools for mitering or coping the tubing like that, but in a nutshell, same thing with a drag car, right? Or a dirt track car, things like that. You can build an entire chassis with minimal tooling. So that's one of the reasons we choose steel. There's some other reasons I'm going to get into in just a minute, but it's also extremely forgiving. Okay, the comparison I typically use is carbon fiber. Carbon fiber is amazing, or specifically we should say carbon fiber composites. Unbelievably strong, unbelievably light. But if you overstress it, you might get some warnings, right? A couple of pings here and there, but most of the time it just bang into two pieces. Okay, but steel, it bends, right? Ideally, it bends before it breaks. Okay, it's the same idea like a roll cage in a car. If you crash and the structure bends but doesn't break, that's a good thing, right? It's absorbing that energy. It keeps the occupant alive. It's the same reason that I have a lot of students that get angry about cars. You get in a 30-mile-an-hour crash and the car's totaled. But back in the day, if you got in a 30-mile-an-hour crash, you might die, right? Because that crumpling absorbs all that energy. So that's one of the big things that we strive for with steel, is it just provides us that benefit of essentially just knowing that it's not going to fail without warning, right? Now, this slide here I put there, some of y'all are way more qualified and more educated than me. But I put this here just to go over some of, I like to say, lay down the ground rules. Because I teach a metallurgy class over here at Blue Ridge, and I always joke around with my students that the state requirement that I'm supposed to teach them is like 2 sentences. But it takes me the entire semester to teach that whole 2 sentences. Because it's just a lot of background knowledge, and we're going to build up 4 or 5 layers before I actually get to my point. But I promise I am getting to my point. Okay? So some terminology. When we say strength, in terms of metallurgy, we're generally just referring to tensile strength. Like if we put it in a machine and we pull on it, how many pounds of force does it take per a given area? And we say that in KSI or thousandths of pounds per square inch, right? So like 70,000 psi is what we would say. So that means if you have 1 square inch of that steel, it'll take at least 70,000 pounds to pull it apart in a straight line. The reason we use that is it transfers over to all the other failure modes as well. You know, shear, bearing, tension, compression, all those, we can correlate them together. And the tensile strength, it just makes it easier to, you know, say that this steel is good for 36,000 or this steel is good for 84,000. You know, it's a good way of doing it. The next one down there is ductility. So, you know, Webster's dictionary, whatever we want to call it, we could say it's how much the material can bend before it breaks. And this includes permanent deformation, right? So it's bent and it's like taking that shape and it's permanently bent forever. Okay, it's a little bit different than what we call elastic deformation, which is it springs, you let go and it, you know, springs back, goes back to its original shape. But ductility is really important for that point I kind of just talked about, you know, when I compared it to carbon fiber, is most of the time, almost all the time, ductility is very desirable, okay? Like we want that extra overhead of safety margin. You know, if we were to actually do it on a graph, which I didn't prepare any today, but, you know, if we're on the bottom 20% of the graph, you know, that's where we live 99% of the time, okay? But if something bad happens, we have that extra overhead of wiggle room to keep us safe, okay? Now the next one down there is hardness. Everyone knows what that means. I will say, you know, when I was in school, they taught me the Mohs hardness scale, where you scratch 2 rocks together. But for metallurgy, that's not quite granular enough. So we define it as resistance to indentation. Okay, so y'all probably heard some of those terms before, like Rockwell C or Brunel or Vickers. There's a number of different tests for it. But it's all telling us the same thing. It's how hard the material is, right? So the next one down there, the fancy word we use is modulus of elasticity. That's basically a measurement of how you can think springy the material is. So within the elastic region, like no permanent deformation, it's how much force it takes to bend it a certain amount. Now this is a tangent, but the really fun thing about steel is that it's linear. Okay, it's called Hooke's law. So if it takes 10 pounds to stretch it 1 inch, it'll take 20 pounds to stretch it 2 inches. It's actually really wild how linear it is. But obviously once you get up to the yield point where it starts permanently deforming, we just throw that out the window, okay? The next one on there, brittleness, or is it brittle, right? Again, y'all know what that means, piece of glass, right? So you bend it, and glass will bend a teeny tiny bit, but then it just explodes, right? Goes into a million pieces. It does not permanently deform, or plastic deformation, as we like to call it. And then the last one, toughness. This one's really difficult. The definition is the ability to absorb energy and to deform without breaking. I kind of already talked about it, like with the roll cage and stuff like that. But a lot of my students, you know, I'll spend probably 2 days of class just talking about toughness. The best example I always think of is horsepower. So for horsepower, you have to have, because of the calculation, you have to have RPM and torque. Okay? If you're lacking either one of those, you don't make good horsepower. All right? So it's very similar with toughness. You have to have ductility and a high strength to get good toughness. Now some materials have exceptional toughness, but it's only because of their ductility. Like one of the toughest, I'm born and raised here in Western North Carolina. One of the toughest materials out there is actually copper, just because it's so ductile. You can bend it into a pretzel, tie it into a knot, and it doesn't break. So if you actually do a test of toughness, again, copper is actually one of the best ones you can get, but I mean, it wouldn't make a very good landing gear. You have one good landing, right? So the next one here, talk about heat treatment. Okay. So again, I promise I'm getting to the point. Okay. But heat treatment is really important because essentially it's how we change some of those properties that we just talked about. And the really interesting thing about it is that certain steels, like let's say 1095, just like a high carbon knife steel, depending on how you heat treat it, you can use that exact same steel for a knife or a screwdriver or pry bar or even like a center punch or a cold chisel. Okay? And most of y'all know what happens if you try to use a knife as a screwdriver, right? It breaks. Okay? But if you change the heat treatment, then you can have it, you know, turn it into a screwdriver or a pry bar, or, you know, obviously there's other differences of center punches and cold chisels, but same idea. You can use the same steel for a vast amount of applications. But again, kind of as I mentioned with a knife, it's extremely strong. It'll hold an edge forever, but it's probably not something that you want to use as a structural component, okay? So, we're going to talk more about that, but also a really big point, I'm skipping ahead to my key points here, is that properties change from heat treatment. You can't really change them in isolation, okay? It's like robbing Peter to pay Paul, or another saying, there's no free lunch, okay? It's like if you get the highest strength possible, you're typically also going to increase the hardness and thus the brittleness, okay? So it's like you kind of have to pick and choose, right? You can't necessarily have the strongest material ever that's also the most ductile material ever. Like the example I just used with copper. It's one of the most ductile, but it's extremely soft. Okay, so they're trading with each other constantly. And we have to, what's another good saying? Engineering is the art of compromise, right? So anyone, myself included, you know, I could build a replacement for the Golden Gate Bridge that would never fail in a million years, but it's going to take a few billion yards of concrete to do that, okay? But it's not practical, so we have to compromise. I mean, that even goes back to, you know, talking about why we choose steel in the first place. Like, why don't we just use titanium? Well, it's really expensive and it's much harder to weld. So it's possible, but again, like steel is it's a good middle ground for a lot of different things. The last point, again, if y'all don't know this, when we're talking about steel, it's iron and carbon. That's it. You know, that's the bare minimum, you know, bog standard, the Laura Lynn brand steel, okay? But carbon is the main alloying element. And if we keep adding more of it, that changes how much we can heat treat it. So on this next slide, I put some numbers here. There's going to be a test at the end, so make sure y'all write it down. But down there at the very bottom, you know, the 0.05 to 0.3, and I just remembered I was given a laser pointer. The 0.05 to 0.3, we call that low carbon steel, or mild steel is probably a term that y'all have heard before. So we use that for the hangar that we're in right now. Okay, it's very cheap, it's readily available, but you can't heat treat it. Even if you try really hard, I do this demonstration with my students, we'll heat up metal till it's almost melting and dunk it in a bucket of water, pull it out, and it still bends the exact same. So, is it best practice to do that? No. But, again, it's not necessarily heat treatable. So in the middle there, 0.3 to 0.5%, that transforms it into something that we could turn into a shovel, or an axe, or maybe even like a machete, something like that. It allows us to actually heat treat it, boost the tensile strength from like 36,000 psi, potentially up into the 50s or the 60s. We can get a lot more strength out of it, and a lot more in the case of the examples I just gave y'all, you know, hold an edge or things like that. And the last one down there, 0.6 all the way up to roughly 1%, is high carbon steel. So that's something like a knife blade, or, well, basically just tool steel is kind of what we call it at that point as well. And as a fun aside, if y'all ever get into the most random trivia competition ever, beyond 1%, we can't, it's roughly like 1.5 or 1 point, somewhere in there. You can't actually put any more carbon in it. And if you go all the way up to like 2.5%, we call that something else entirely. It's called cast iron. Okay, so what actually happens in cast iron is, I like to say it's like my my Aunt Roxy's sweet tea. I promise I'm going somewhere with this. When the water's really hot, she dumps a whole bunch of sugar into it. Way too much. Okay? But then once she puts it in the fridge and it cools down, that sugar actually settles back down at the bottom. It precipitates out. The exact same thing happens when the dew point gets lower than ambient. It starts raining. Okay, so in cast iron, you have way too much carbon, but then as it cools, that carbon precipitates back out into graphite. Okay, so that's one of the reasons that cast iron is just wonderful at machining. You know, drilling or turning on a lathe or milling or anything, it's self-lubricating. It's already full of graphite. You know, the same stuff that you put in your lock when it gets sticky. Anyway, I like tangents. So, it's a fun one. So with all this being said, what actually is 4130 tubing? So 4130 is AISI, SAE. They actually teamed up for, you know, once and forever. Two different standards actually decided to unite instead of creating 5 other different standards. But they united and said, yeah, we'll both use this. But it's basically the designation for steel that has some chromium and molybdenum added to it. And again, we call it chromoly, or just 4130. anything else. And the reason that it's so absolutely ubiquitous is it's a really good mix of all the properties for it. So strength to weight, workability, and also cost. Now, I will say, interestingly, I think cost is more due to economy of scale, right? Because if you look at even just similar alloys, like a 4340 or 4140, very, very similar, just slightly different amounts of sugar and spice added to them. They're vastly more expensive. But again, 4130 has been used in things for, oh gosh, I don't even know how many years. Very long time. Now, the fun part here, when we're talking about 4130 tubing, is if you look it up online, you might think it's a low carbon steel because it's only roughly 0.3%. And on that last side, what did I say? It's 0.05 to 0.3. So you might think like, yeah, it's not heat treatable, so that means we can do whatever we want with welding it. But there's a really fun problem called carbon equivalency. And here's a really scary equation. Yeah, this will be on the test at the end. But all this means is we take our percent of carbon and we add up everything else. So manganese, silicon, chromium, molybdenum, vanadium, copper, and nickel. Now I personally have it completely memorized in my head. No, I don't. Okay. Now if I ever have to know this, I just look it up. Okay, or nowadays you go to ChatGPT and say, what's the carbon equivalency of 4130? And it just does the math for you. Yeah. Okay. So, but it ends up being right around 0.64% for 4130 tubing. And again, I don't even know if I said it already, but we use this as a reference, okay? It's not like a cut and dry, perfect thing. It's more of just a reference that kind of tells us what might happen if we heat treat it, either intentionally or unintentionally, okay? But at 0.64%, that puts it really deep into the danger zone, okay? And it's not the Kenny Loggins, the fun one, the fun danger zone. But AWS says anything above 0.4%, if you weld it wrong, has a potential for brittle failures. And you remember, brittle failures are the scary ones. It's failure without warning. But also, from another source I found, I didn't write who it actually was, but they classified anything over 0.5% as poor weldability. So, again, we're almost to the point. So an overview of some of the basic heat treatment. If y'all have never seen this, like if you've ever watched Forge and Fire or any other blacksmithing sort of things, this is a super basic cut and dry how it works. The first step is we normalize it or anneal it. These are essentially the same thing. The crude way that I tell all my students is annealing is the really high quality, normalizing is what you get from like Temu or Wish.com, okay? But in practical terms, annealing is essentially done in a furnace where you heat it up all the way up to roughly 1400. There's a magic number there, it's a critical temperature, and you cool it as slow as you possibly can. That gets us the metal that's as soft and as ductile and malleable as it can possibly be. I didn't talk about that terminology, malleable, but for the purpose of right now, it's very similar to ductility. And you can also think of it like a factory reset on the metal. So at any point, like if you're heat treating something and you screw up, just start over. Like you can do that unless you crack it or something like that. You can pretty much do it as much as you want. And there's obviously other problems and limitations, but in theory it's resettable. Now the next step typically in heat treatment is a hardening stage, or it's commonly just referred to as quenching. So you heat it up to that same temperature all the way above critical and then cool it as quickly as possible. You know, a bucket of water or oil or sometimes just forced air, a lot of different methods. But the point is we're cooling it as quickly as possible instead of as slowly as possible. What this gives us is a metal that's extremely hard. It's as hard, strong, and as brittle as it can possibly be. So it might be really useful for a old school like straight razor, but again, the structural component, probably not. But the last step, tempering, most of y'all have heard this terminology before. You know, if you've got an old axe head that you throw in a fire to burn the broken handle out of it, your grandpa probably told you that it'll lose its temper, okay? But what tempering is that we heat it back up just a little bit, and it trades some of that hardness and strength for a little more a little more toughness and ductility. Okay, so again, we're robbing Peter to pay Paul, right? We went all the way to the maximum, and then we bring it back just a little bit. Or that's why that terminology is also used in a lot of other things. The first example that comes to my mind is, when your uncle makes a jar of moonshine and tempers it back a little bit so you can actually drink it, okay? Add some water to it, okay? So, yeah, these are kind of three basic steps. But also with tempering, the nice thing about it is that's where we get all that versatility from. That's how we can take the same steel that's used for a knife and also make it into a pry bar. It's just varying that temperature. And I put a maximum of 600, because generally speaking, 400 degrees Fahrenheit to 600 degrees is kind of the magic range there. So something like 400 would be, say like a razor. 450 to 500, that might be a pocket knife. 500 and up, that's going to be tools like chisels, punches, a shovel, things like that. You ever heard of the brand True Temper?
Yeah.
Yeah, that's where the name comes from.
And those numbers are particularly for that type of steel.
Yes, so this,
Aluminum would have different numbers.
Yeah.
Okay.
Yeah, aluminum is, the fun thing about metallurgy is once you learn a whole lot about steel, you basically start over from scratch for aluminum, and then you start over from scratch again for titanium. But yeah, aluminum heat treatment is very similar, but also quite a bit different. A lot of aluminums are what they call age hardening. So you might do an initial normalizing, annealing, or even quenching, but you actually just have to let it sit for a few weeks. The really, really crude example, as I always say, is kind of like concrete. Concrete, you can walk on it after a couple hours, but it never truly gets its full hardness, ever, right? It's an asymptote. It goes up and then just stays there forever. Okay, so a lot of aluminums are very similar, but there's also different types too. So that's one of those things that, gosh, if I even had to summarize, say 6061 T6, that's a super common aluminum. That T6 refers to the heat treatment. The fun thing about it that a lot of motorsports guys don't realize is as soon as you weld on it, it's no longer T6. Yeah, you've reduced that hardness. But over time, it will slowly come back. But aluminum also has other properties that, again, I didn't even put it in this presentation, but aluminum has what's known as an infinite fatigue limit. That sounds like a good thing, but it's a bad thing. So what that means is that no matter what you do with aluminum, no matter how much you stress it or how little you stress it, it will eventually fail. Okay? With steel alloys and titanium, there actually is a limit that if you stay below that fatigue limit, you can fatigue it forever, like indefinitely. Okay? Now, practically speaking, with aluminum, that limit, it may be so far down the cycle that it may take 100 years of constant use, right? So it's not like a scary aluminum is bad. It's more of just an interesting thing, especially if you overstress aluminum, you will start to see cracking on it a lot of the time. A really good example of that is a student of mine brought in is a forklift. It's like a ramp thing to bridge in between the loading dock and the back of the truck. Had a big crack in it. We started welding it, and I got halfway through the weld, and it sounded like somebody just hit it with a hammer because it cracked from the other side. And we're basically just chasing on the cracks. Okay, and we gave it a good effort. I told him it probably wouldn't work, but yeah, we gave it a good effort. But sometimes, once it gets to that point, you just have to scrap it or hang it on the wall, right? So with all this being said, one of my catchphrases, I'm going to coin this and patent it and copyright it. But welding is just accidental heat treatment. Okay, that's all it is. Okay, I mean, yeah, we're joining metal together, but you can think of it like it's accidental heat treatment. Because for heat treatment, I put them backwards here, but we're only using roughly 400 degrees Fahrenheit to about 1400, maybe a little bit higher than that. But welding goes from ambient, whatever it is, like 75 right now, all the way up to 2800. That's the melting point of steel, and potentially much hotter than that. So you can imagine if you have a heat-treated steel and you weld on it, it's kind of like the Wild Wild West, right? It's going to be all over the place. We don't know what's going to happen, do we? But we can predict it. We're going to talk a little bit more about that. But that's really just a key. If you forget everything else, I got a whole slide at the end if you forget everything else. But if you forget everything else, just know that with welding, we're going to change the properties of the steel. There's no ifs, ands, or buts about it. The best thing we can do, though, is understand what's going to happen, and that's going to allow us to make sound engineering decisions. so we can either minimize the damage or potentially even use it to our advantage, right? So I've got a hypothetical situation here on the next slide. Purely hypothetical. We have two different scenarios. So this is kind of getting into what I was talking about with, welding advice on the internet. A really common thing that people do is they try to, with TIG welding, I don't even know if I said that at the beginning, that's kind of the general context, but a lot of people try to use the least amount of heat input possible. So they try to get in, get out, cool it down fast. And so they do that a lot of different ways. One way in the bicycle frame building world is they'll actually make heat sinks that go on the inside, made out of copper or brass alloys, so it sucks all the heat out really quickly. They'll also just use really good technique, relatively speaking. And also they may use, if y'all have ever heard of like a pulsar on a TIG welding machine, it essentially varies your current up and down really fast. And you can change the rate at which it does so. I could talk about that for a very long time. But again, they try to minimize that heat input and also get that heat out of it really fast. But then scenario two, what if we just use a really generous heat input and then allow the metal to cool down nice and slowly after we weld it? So again, this is purely hypothetical, and it has nothing to do with these two pictures. All right, I'm bad at sarcasm, okay? So this is exactly that scenario. This is one of my welds. Don't look too closely at it, especially that crater. This is not one of my welds, and I stole this picture from Instagram. I don't really want to give him credit because I'm going to roast him. Now, if y'all can see those two different welds, he's a much better welder than me. Okay, I struggle my way through, but this guy's an absolute artist with it. He has a ridiculous amount of skill, but I've seen his process. He posts it very publicly on Instagram. He's quite a big person in the bicycle frame building world, but he also gives really bad advice because he does all of those things for 4130 where he uses a pulsar to minimize the heat input. He uses heat sinks on the inside to suck that heat out as fast as possible. And also, something we haven't talked about yet, he uses the wrong type of filler metal when he welds it. So all those things combined, he has an extremely high probability of his welds being very hard and potentially very brittle. Okay. Now, does that mean his bicycles are going to fail and you should never buy one? I don't know. Probably not. Okay. It's one of those things that, we talk about this a lot in welding and just engineering in general, but there's best practice and then there's good enough for the real world. Okay. So realistically, his welds are probably good enough for the real world. He's a very popular person. He's sold hundreds of bikes, and as far as I can tell, no one's ever posted a failure of one of his frames online. Now, another thing that I'll say, I didn't put the picture here, but I got a picture of me taking my bike off a jump that I immediately crashed after. The way that I ride my mountain bike is, I'm 220 pounds, which is overweight in mountain biking terms, and my riding technique follows any trail is technical if you ride it wrong enough. So, I don't know. And again, it's a very esoteric conversation, but again, you can also even see, if y'all have ever seen some of these pretty colors around welding, most people that have been, it sounds a little bit pompous, but I'm going to say classically trained, would say that my weld has a really bad heat affected zone compared to his over here. And that's something I may just talk about at the end. I didn't put it in my presentation, but heat affected zone, or at least the pretty colors, are correlated but not causated. Is that a word? It's an Appalachian word.
Yeah.
Okay. So again, he's probably doing it just fine, but I will say with 100% certainty, I would never get in an aircraft that was welded like this, especially when you can consider things like fatigue. Bicycles, they go over a lot of bumps, but they don't have engines. Okay. So, a whole lot of different stuff, but I talked about heat input, so real quickly, I'm going to give y'all more math. I really like math. It defines the world that we live in. But heat input, when we say that, is we're basically just saying how much heat do we put in the metal. Okay, for electric arc welding, this is the equation: volts times amps times 60 divided by our travel speed. It's an extremely simple equation. If you're curious, this 60, it's because we're doing inches per minute and we're doing kilojoules, so it's just a constant there. But also for welding, if y'all have ever done any welding with TIG or stick, you know what amps are. It's the setting on the machine, okay? Or in electrical terminology, it's the volume of water that's flowing through the pipe, right? I don't like the water analogy, but it works, okay? Voltage, we can think of it as the pressure of that water, okay? Or in welding terms, it's our arc length, okay? So they're directly correlated. With TIG welding, we have the tungsten off of the base metal. How close we hold it or how far away we hold it tells us the voltage. You can actually, if you get someone else to weld and your machine has a digital readout, you can watch it and you can judge them based off of what their number is, okay? But the reason that I give this equation, this is the part where a lot of my students get scared when I give them the equations, and especially the carbon equivalency one. But the important part here is it tells us what affects our heat input. So if we want to minimize it, this is a totally different conversation, but if we want to minimize it for like stainless steel, we would keep our arc length as tight as possible. We'd lower our amps and we'd go fast with our travel speed. It gets really weird though with TIG welding in particular, because sometimes more amps can allow you to go faster, which overall reduces the heat input. So it's kind of a, again, it's like a give and take, right? But in the case of 4130 tubing, we don't want to reduce our heat input as much as we can. It's actually better to just not worry about it and be kind of generous. Take your time, let the heat just soak the whole joint or the whole cluster, and just let it cool down really slowly, okay? Now, again, that equation just tells us how it works. But another really important part that we already talked about with heat treatment is the cooling rate, okay? Because if y'all remember, the quenching or the hardening part of heat treatment is we go up to roughly 1400 or a little bit beyond, and then we cool it as quickly as we can. And if we're welding at, what was my number, like 2800, we'll just say 3000 degrees. We're going well past the danger zone, okay? So we want to do that as slowly as we can. The way that we actually minimize that is based on a lot of different factors, but the best advice I can give you is don't be afraid to actually preheat 4130 before you weld it. It's just best practice anyway, especially if it's not summertime, okay? Like if it's anything below 50 degrees, that number actually comes from AWS, but if it's anything below 50 degrees, you should preheat it. Especially considering in the wintertime, most workshops, we don't have air conditioning or heating in them, so there's probably gonna be some condensation as well. So go ahead and get just like a plumbing torch, that's what I use, even just for a few seconds, just kind of knock some of the chill out of it, get it to where it's nice and warm to the touch, and that's gonna help you out tremendously. It'll take away a lot of the worry. But thickness is really important too. Okay, so most tubing, for bicycles and everything else, is really thin. So as soon as you light up on it and start welding, the whole thing's going to be saturated with heat. It's going to be red hot by the time you're done. But in this case, that's a good thing, right? We want that. But if you're welding something thicker, you can think of it just like it's a heat sink all of its own, okay? So all that heat is going to get sucked out to the cold parts of the tubing really quickly. So again, best advice, go ahead and put some heat into it, right? If you heat up that steel to 100, 200 degrees, the delta or the difference in your temperature is much smaller. So the rate of change is slower, okay? So again, that's a really key takeaway too is, again, don't be afraid to go ahead and heat it up a little bit. Make it too hot to touch before you weld it. Now again, something like stainless steel, that's the opposite advice, okay? So another thing in the bicycle frame building world, there are stainless components. And there's even a big thing now in bicycles, like that chainstay yoke I showed 30 minutes ago, okay? A lot of people 3D print their own, or they outsource it, but 3D printed out of metal. Okay, the technology exists to a point where you can upload a 3D file online, pay $50, and a week later you have a 3D printed metal part in your hand. It's insane. But most of those are 316 stainless. Okay, so now I just told you that 4130, we want to maximize the heat input and slow the cooling rate, but stainless is the opposite, and they're often joining those two together. Okay, so a lot of people are asking me, what should I do? And I told them, I was like, I have no idea.
Bolt.
Yeah, do the best you can, right? Now, realistically, the differences aren't that great. Again, we're talking best practice versus good enough for the real world, okay? Actually, one guy recommended he just braze it instead of welding it.
Carbon fiber electrical tape.
Duct tape.
Now the last advice I'll give, well actually, now that you mentioned, a lot of bicycles, they do the lugged frames or the 3D print. You can think of it just like a socket and then glue in a carbon fiber tube. It works well. Yeah, if you use the right epoxies, it's extremely strong. Yeah. And a filler metal for TIG welding. So if you Google what is the best filler metal for 4130 or ask AI, it's probably going to tell you this one right here, the ER80S V2. Because on paper, 4130 is roughly right around 80,000 PSI. I think it's like 84, depending on the heat treatment. And so they say, hey, this one's 80. 80 matches 80, right? That's a good thing. I don't want to go less than that with 70, okay? But it's generally not a good thing, okay? Especially with thin wall tubing, our welds are oversized, okay? So what that means is that if we have a tubing that's 60 thou thick, or roughly a 1/16 of an inch, and we put a fillet weld on it, like some of the pictures I had earlier, that's way bigger than 1/16. So that weld has double or even triple the volume or cross-sectional area of that tubing, so it's going to be much stronger. So it's actually better to undermatch our filler, because what that gains us or gives us is more ductility. Okay, again, ductility means safety. That's a really good summary too. It gives us that wiggle room or that safety margin. If you're really interested, I would recommend this one, the Dash 2 variant. Dash 6 is the most common, but Dash 2, well, the difference between them is the deoxidizers in the filler metal. So Dash 6 is really common with MIG welding as well. It's the exact same filler wire as TIG, but it has a lot of silicon. The Dash 2 has 3 others. I forget which ones. I think aluminum, titanium, and something else. But anyway, it's actually meant for open root welding without a purge, which is what we're doing on the tubing, okay? So we're welding, it's a full penetration joint. We have our argon shielding gas on the outside, but we don't on the inside. I mean, you can if you plumb it up and tape it off and everything, but generally it's just not needed. Okay, and the Dash 2 wire is actually meant for it. And some welders say that it welds better. I've never noticed the difference. If you blindfolded me and I did an A/B test, I doubt I could actually tell. Okay. Now, this is my last slide here, or maybe the second to last. These are my key takeaways. Okay. So again, if y'all forget everything else, rule number 1 is know what you're welding. Okay. And this morning at like 5 a.m., one of my dogs woke me up. I'm sitting there reading the advisory circular 43.13. You know, as one does, right? That's normal. That's normal in this building, I hope. You're sitting there reading it at 5 a.m. It says very similar in there. Okay, know what you're welding. It says something to the effect of look up what the manufacturer made it out of, or if it's like a, fully custom, well, what did you make it out of, right? Is it just mild steel? Is it something you found outside in the scrap bin, right? You got to know what you're welding, because it makes a huge difference. Speaking of that, know what you're welding, depending on how old it is. I was involved on a project in my last company. I was doing some non-destructive testing on the Peter Geist Bridge. That's the one on 26 right before Saluda. I don't drive across that bridge if I can avoid it.
We have to.
Well, I live on 176, so when y'all pass my house, just honk and wave. They disallowed any hot work on that project because they actually took samples of that bridge, did some testing, and figured out the carbon equivalency was, they didn't tell me the number, but it was scary high. Because that bridge was built in the 60s by railroad engineers.
Cast iron?
It wasn't quite that bad. But I can tell you that bridge also, it was fascinating being under it, because they had repairs and non-destructive testing going back to the 90s from what I could tell. So it was pretty fascinating. Also, random tangent, there's an eagle nest in there. Because they had these catwalks under the bridge, and there's a nest this big. From one of, I think it's the golden eagle maybe. Yeah. But anyway, so they disallowed any hot work on that bridge. So everything that they're doing, they're adding the structure in between and the deck on top, it was all drilled and bolted. Which can be just as strong as welding, like, don't misunderstand that. But the point is that steel was so old, that the engineers said, absolutely not. Don't touch this thing with a welder, a cutting torch, or anything else, or even a grinder, I think they said. Like they wanted, if I'm not mistaken, they were drilling all the holes, and then to deburr it, I think the engineer said only sandpaper discs, like the layered flat discs or anything like that, because the regular grinding wheels they have a pretty localized heating area to them. So it was fascinating.
Wow.
Drill without heating it.
Well, it does heat a little bit, but they were using the, what are they called? I just know them by the name slugger. Annular cutter, that's the word for it. So it's kind of like a hole saw, but it's specifically meant for drilling, like with a mag drill. So it's a drill press with a magnet that sticks on that, and then it has think of it like a hole saw. So it actually pulls a really nice chip, at low speed, instead of the way that I drill things, which is floor it and push as hard as you can. So, yeah, really fascinating stuff. But, yeah, so know what you're welding. It's vastly important. Because, again, how do we know or make any sort of decisions about our process choices if we don't know what it is? Okay? I don't know, I'm completely guessing, but y'all correct me if this is off base, but would y'all just jump in an aircraft and fly it if you don't know any of its history? Or who?
Sounds
Sometimes the
interesting.
mission demands it.
So, I mean, it's similar to that, right? So, I tell all my students the same thing when, if any sort of vehicle or trailer or life supporting equipment or anything like that, if they get asked to weld it, that should throw up a lot of red flags. 99 times out of 100, it's probably fine. But there's also a really big case study. If y'all get really bored, it's like an hour long, but a video about it. But there's a gentleman that welded on a lowboy trailer. So it's one of the trailers that disconnects on the front. You drive the excavator on it, and it only picks it up like 6 inches off the ground. And it was made out of a steel called T1. It's a really common steel in the, don't quote me on this, but 70s. It was super strong. They use it for air compressor tanks, boiler vessels, everything in trailers. But the problem with it has multiple problems, but the carbon equivalency is really high, and it also has a nasty habit of cracking after you weld it. And not just right after, but like 24 hours after. So you'll go cool down to ambient, you'll go home, come in the next morning, it's cracked. Okay? But anyway, a gentleman did a repair on it, and all things considered, he did a pretty good job. Okay? Like he gouged out the crack properly, removed every single bit of the crack, welded it back up, put a fish mouth plate, it's kind of like a diamond. They put sideways, it's real common on things like that. Welded it all out. But he didn't preheat it. He didn't do any post-heat to slow it down even more, and he used the wrong filler metal. So, I know I've been joking around a lot in this presentation, but unfortunately that trailer, it became so popular because it was hauling an excavator down the interstate. That repair broke, and it killed a family on the interstate. So, I tell my students all that story because it's one of those things that even if we think we know what we're doing, we might be right at the top of the Dunning-Kruger curve. Y'all are familiar with that, right? So I wish I had something to draw it out, but it's competence and confidence, okay? Once you first start to learn something, your confidence skyrockets. You're on top of the world. And then typically you get humbled, okay? And you shoot all the way back down to the bottom. And then over the years, you slowly climb back up, okay? So I like to think I'm on the second upslope with welding, but I might very well still be on the first. I'm not sure how that works. But yeah, so again, I used to do a lot of rope access and working at height, and I had 2 or 3 different experiences that humbled me. Just things that, like I always share one that I was in a boom lift, 70 feet up. We were going up and down the building, all the way down the side, driving up and down, everything. We're up there for probably 45 minutes doing an inspection. I get down, and I had my harness on. I went to unclip myself, and I'd never clipped myself in the first place.
Whoa.
It's scary. It's all it takes is one little mistake. But so the first one, know what you're welding. Second one is know how it will react to weld. Okay, so again with 4130, we already know now we don't want to cool it down quickly. We want to get it nice and hot and let it cool down as slow as we can. Okay, even if that means taking something like an insulating ceramic wool blanket, just don't breathe that in, it's really bad for you, or like a fire blanket, and just wrapping up your weld after you're done. Old blacksmiths have a trick when they're making tools. If they want to anneal them, they would have a bucket of vermiculite, If you've never heard of that, it's a really common, I guess you could call it additive to soil to help it aerate, if I'm not mistaken. I'm getting a nod back there, so. But it's really fluffy and insulating. So they would heat up their tool red hot, dunk it down in there, and then the next morning you reach in there to grab it and it still burns you. Like, that's how good of an insulator it is. So you can do stuff like that and let it cool down really slow. And the last one is know why you are welding it. I didn't really talk about this at all in the presentation, but still really important. Repair welds are a lot different than new fabrication. Okay? And most of y'all probably already know this in the back of your mind, but if you think about it, if you're building something new, actually let me back up. So let's say you have a trailer that you, I don't know, backed into your workshop or something like that. It dented and bent one of the tubes on it. Well, you cut it out and weld a new one in there, right? I mean, yeah, why not? Second scenario, what if you have a weld or a tube that cracked and there was not like one event that caused it to crack, okay? Like maybe you landed a little bit too hard, you got a crack, okay? That would be an event that caused it. But if you don't know why it cracked in the first place and you just weld it up, it's probably gonna crack again, right? Okay, so generally speaking, if you have a failure either in the metal or in the weld, and there's no event that leads to why that happened, that's a huge red flag. Because that actually points to an engineering failure or design failure, okay? Like that tube or that weld is not suitable for the task. But again, if you did something silly or dumb and you broke it and you know why, then yeah, just fix it, okay? But I run into that quite often. You'll also see guys that, you know, something breaks, they weld it, breaks again, they weld it again, and so on. And they think they're a horrible welder, but in reality, it might very well be the person that designed the thing in the first place. And we kind of already talked a little bit about that with aluminum, right? So sometimes aluminum just reaches the end of its usable life, okay? Yeah, that's a really important one. I try to stress it to, you know, get a lot of my students, they're 18 years old and, you know, on top of the world and on top of that Dunning-Kruger curve, okay? So I try to just teach them to at least, you know, use the thing in between their ears, okay? You know, think about what you're doing. Or even gosh, like one of the hardest things to teach my students after they've welded for a little while is not everything is a welding problem. Or a solution. Welding is not the solution to the problem, right? A good example of that is one of my students, we replaced the tongue on his trailer. Something happened. Yeah, I think he like did something dumb, dented it, wouldn't lock very well anymore. So he went to Tractor Supply, picked up a new one. He's like, yeah, I'm gonna weld it on there. I was like, I won't say his name. I was like, Bill, right? I'm gonna call him Bill. I was like, this thing has holes in it. You're supposed to bolt it, okay? So we drilled 2 holes and we bolted it on there, okay? You know, especially in that case on a trailer, and the way he was loading that trailer, I feel much better with even grade 5 bolts than, you know, a few welds on it.
That's so when he smashes the next one, it's faster turn.
Yeah.
Faster repair.
New bolt. Yeah. All right, so that was all I had. Okay. Now, I will say something I always tell my students as well is I just gave y'all a presentation. I'm going to assume it's the best one in the world, but the real learning starts with questions. Okay.
So thank you, that was awesome to hear. I understood some of it. When you look at using stainless steel versus 4130 in an airplane, for example, I've always been of the information that stainless steel cracks much more than 4130, and you should always use 4130 in an aircraft frame. Can you talk about that a little bit?
I think it probably depends on the specific stainless. I do know, well, first of all, I'd actually love to read into that. But I do know that there's some really weird things that can happen with stainless. I've encountered it in the pharmaceutical world. They call it stress corrosion cracking. So depending on the environment, I don't know if it's even applicable for an airplane, but if it's an extremely severe environment, the corrosion can actually get in between the individual grains of the stainless and essentially work its way all the way through to the point where it will crack. And we saw that a few times actually in some of our inspections. So, and we would do the penetrant testing, the non-destructive penetrant testing, and it would look like a spider web on the surface.
Oh, great.
because in between all the grain boundaries, it would corrode its way through. So I'm guessing that could be correlated to it.
And what about the, whatever the strength is called, if this is a beam and you're looking at this dimension, how do you compare stainless with 4130?
They're probably very similar. If I'm not mistaken, I think the modulus might be higher on stainless than on 4130. But anyway, yeah, I'll just look at the modulus because that will tell us, for the regime that we care about, not failure, that's the stiffness of it. So if you compared, again, I actually checked earlier, I don't have internet service here, but if you looked at a chart of the two materials and compared the two, whatever number is higher on the Young's modulus is going to be stiffer. But also, again, we have to simplify because some of y'all are probably real engineers in here. But if you have a beam and you bend it, the top is getting pulled apart, the bottom's getting squished, the middle is doing all kinds of stuff in between. It's similar with tubing, but with tubing you also have the buckling failures, which is I can't even wrap my head around that math yet.
And then you've also got the issue of welding that you were talking about, right? And how that heat treats the material
Yeah.
and how you weld it is going to affect the propensity for cracking.
And that's another thing I actually forgot to put in my presentation is the stresses in welding. So a really nice or a bad thing about welding is this molten super hot. As it cools, it shrinks. Right? So you create internal stresses inside that material. The really nice thing about taking your time with the welding, let it cool slowly, is it gives us a chance to relax. I'm sure a lot of y'all are familiar with gas welding on aircraft frames. So I say back in the day. Back in the day with gas welding, they would weld it, and then you would sit there and just gently heat the whole thing for a while. They're basically just normalizing it. So that relieves a lot of the stresses. So that could be correlated as well with stainless. If you get in, get out, the stresses never have a chance to actually be relaxed or relieved. So yeah, that's something I didn't even put in there. It's probably in my book somewhere though.
Well, how do you get your book?
Well, I was telling some of y'all earlier, it's on Amazon, but if you want it, send me an email. I'll send you a copy of it. Okay? Yeah, because this book here, it's on Amazon. I think it's something like $19 or $20. But I will say, yeah, if you